Good evening and welcome to you all. Welcome to another Durham Castle Lecture. We've had a fantastic term of packed audiences in the Great Hall. It's been absolutely a delight to have a lecture series to which so many people, including local people, attend. And I'm sure this evening will not be disappointing. We search far and wide across the world for the most engaging and significant speakers to invite to the Durham Castle Lecture Series. And over the last 5 years, a fair representative sample have been here, attended, given lectures, which are filmed and then watched across the world. But sometimes you don't have to search far and wide. Sometimes the person one is looking for is no further than one's backyard. But sometimes, yes, it's in no further than one's backyard. And in introducing Carlos Frenk tonight, I'm introducing not just one of the brightest stars in the Durham constellation, but one of the very brightest stars in the whole field of cosmology. Professor Carlos Frenk is director of the Institute of Computational Cosmology, Durham University's world-renowned theoretical cosmology research group. Along with collaborators from all over the world, he has built model universes in the state-of-the-art supercomputers, trying to understand how the structures of our universe evolved from simple beginnings to the complex structures composed of stars and galaxies that we see today. In 2014, he won the gold medal of the Royal Astronomical Society, and in 2017 was awarded the Max Born Medal and Prize of the Institute of Physics and the German Physical Society for outstanding contributions to physics. But in truth, these are among the many honors Carlos has received in recognition of his remarkable contributions over a lifetime so far, with more to come. So please join with me in giving him a very warm welcome.
Well, thank you, David, very much for that very kind introduction. It was so nice. I was beginning to look forward to my own lecture. But it's a great pleasure for me to be speaking in this amazing place. And it's a particular pleasure to give this lecture on the eve of the opening of this new building that many of you will have seen. This is the building that will house the Ogden Center for Fundamental Physics. It will be officially opened on Friday. And for the first time since the rebirth of astronomy in Durham, all astronomers will be housed under a single roof, all 150 astronomers that we have in Durham. Now, you may have seen the title of my talk. It's slightly cryptic, everything from nothing, or how the universe came to be the way it is. So that's what I'm going to talk about. I was told I have to stand here because the sound is being recorded, but I think I can take this off and walk around, isn't it? Very good. So now so this is the title, it's cryptic. I will explain what I mean by that in a minute. But let me just say, I'm going to be talking about cosmology, and cosmology is a branch of physics, a very special branch, because it asks some of the most fundamental questions that humans have been asking since the beginnings of civilization itself. Questions such as, why does my changer doesn't work, for example? Questions such as, how did the universe begin? What is it made of? How did it evolve to its present state? What does the future hold? These are about the biggest questions that people can ask, and it might not be an exaggeration to say that civilization began when our ancestors started asking questions of this sort. However, and it's not just us physicists who want to know the answers to these questions. Many other people worry about these sort of things. Theologians, philosophers, artists, but the difference is that in physics we have a very well-defined methodology to try and address these questions. And the methodology is sketched here. It's based on the application of the laws of physics. So when I talk about the beginning of the universe, I'm going to talk about it from the point of view, a very narrow point of view of a physicist, distinct from what other branches of knowledge would, the way they would be approached in other branches of human knowledge. So we have these wonderful laws of physics, which are general rules about natural phenomena. They are, for the most part, derived empirically in a laboratory through experiments, and then generalized and expressed in the language of mathematics. For example, many of you will be familiar with Newton's law of gravitation, with Boyle's gas laws, with the laws of quantum mechanics, relativity, and so on. Now, almost all of these, the exception being general relativity, which came out of Einstein's head, but almost all the laws of physics are actually based on experiment. They are empirically derived and then generalized and are used with the language of mathematics, which allows us to manipulate them in very powerful ways. Now, so one of the biggest mysteries that I've encountered in my career as a physicist is the realization that these laws of physics that we learn about, we discover by doing experiments here on Earth, seem to apply not just on Earth, not just in our laboratories, but they seem to apply everywhere and at all times, even in conditions like the Big Bang, which bear no resemblance whatsoever with the conditions in which these laws of physics were discovered. So we refer to that as the universality of the laws of physics. And that to me is as profound a mystery as the fact that our universe exists in the first place. But maybe too far from my computer. So enough of philosophical digression. Now, so I'm going to test the technology here, see if I can get this microphone and get closer to my computer. So we'll obey the, I decide to change slides. So so let me now go back and explain what I meant by this somewhat cryptic title of my lecture. And as I will explain in a minute, cosmic history is a story about nothing. So I'm afraid to tell you, I'm going to spend the next 50 minutes or so talking about nothing. But in fact, this is a very special nothing, because it's a nothing that gave rise to everything. So let me now stop being cryptic and tell you, first of all, that by nothing, I mean something very precise, some concept that is very well understood in physics. And what I mean when I say nothing, I mean something very specific. I mean the vacuum. And the vacuum is effectively nothing. And it turns out, in fact, that the current view of where everything in the universe comes from is intimately related to nothing, related to the vacuum. So let me tell you a little bit about the vacuum. And imagine an experiment in a laboratory. Imagine you have a cavity, and that you have a very, very powerful pump, and you extract everything from the cavity. So keep pumping away until the last molecule has been evacuated from this cavity. You say, well, there's nothing in the cavity. I've taken all the air, everything out. And then, once you've achieved that, and there's no single molecule in that cavity, if you were able to look at it carefully, then you will find something very surprising. And I tried to make a movie of what you will find if you were able to look at this empty cavity. And you'll find that the cavity is actually full of energy. And the energy in this vacuum manifests itself as the spontaneous creation of something very strange, of matter and antimatter, represented here by green and red balls. So out of the vacuum comes this matter and antimatter, but you know that when matter and antimatter collide, they annihilate into energy, which then decays again into matter and antimatter, which then annihilates, producing energy. And this cycle is going on and on in the vacuum, and in fact, it's entirely consistent with the laws of quantum physics. In fact, it is the basis of our understanding on quantum physics. Some of you may be familiar with the Heisenberg uncertainty principle, and that's exactly what this is about. Now, it sounds very odd, and And for those of you who look slightly puzzled, this is the hardest part of this lecture. It'll get easier from now on. All you need to know is that the vacuum is bubbling with energy that comes and goes very, very quickly and producing this vacuum energy. And actually, this can be measured experimentally. There's a very famous experiment in physics called the Casimir effect that actually probes this energy of the vacuum. Okay, so it'll get easier now, I promise. And the proposition of modern cosmology, which is quite a proposition to make, is that, in fact, everything in the universe, galaxies, stars, planets, and us here, came out of the vacuum. And that's what I'm going to be telling you about in the next 45 minutes or so. And that's why the title of this lecture is Everything from Nothing. By nothing, I mean the vacuum, and by everything, I mean the universe. Now, so from the point of view of cosmologists, the building blocks of our discipline are the galaxies. And galaxies, you can see an example here, are collections of stars, anywhere from a few tens of millions to hundreds of billions of stars. Now, and we live in a galaxy very similar to this one. In fact, we are actually located about 2/3 of the way from the center of a galaxy, the Milky Way. The sun is around here, although some of my colleagues in the Institute, when I show them this, they get very upset. They say, what do you mean? We live in the center of the galaxy, but that's not quite true. We live 2/3 of the way out from the center of the galaxy. Now, to get you in the right sort of cosmological mood, I want to show you a movie. Right. Okay, sorry about that. I'll move away so the microphone doesn't interfere. So what this is a tour through the local universe of galaxies. These are all real data. There's only one little bit of artistic impression that I will highlight. And here we are flying in space towards the constellation that many of you will have seen in the night sky, the constellation of Orion. And next to the constellation of Orion is this cloud called the Orion Nebula. It's a cloud of gas and dust, and new stars are being formed in our galaxy at a rate of about one new star every year from the gas and dust in clouds like this. We're going to head for a very well-known nebula called the Carina Nebula, where it shows you that, in fact, let me get rid of this finger. So it shows you that actually stars tend to be born in collections of a few tens of stars. We'll now go and admire a different kind of nebula altogether, because not all of these clouds are birthplaces of stars. Some of them are the opposite. This is a graveyard of stars. This is a star, not unlike the sun, which, however, has run out of nuclear fuel. The sun shines because it has a nuclear reactor in the center. This one has run out of nuclear fuel and has died, leaving behind something called a pulsar that you can see, those of you in the front, pulsating. So here is the only bit of kind of science fiction in this movie, where we leave our galaxy and look at it from outside. Obviously, we cannot do that, but it's a galaxy very similar to our own. Now, galaxies are typically about 50,000 light years across. It takes 50,000 years for light to cross a galaxy. So these are very, very big scales. 50,000 years is a long time, not propitious for snappy repartee. And now we're going to head for our nearest neighbor, large neighbor called the Andromeda Galaxy, which is at about a distance of 2 million light years away. It has a neighbor also with its own clouds of gas and dust that are making stars at a similar rate to that in the Milky Way. Now, eventually, we're going to head towards this clump of galaxies here called the Virgo cluster. Before that, we will take a little detour to admire some of these amazing things that nature has managed to make. Galaxies that are really, really pretty astonishingly beautiful. Here's one that's interacting with a neighbor. And then finally, we head towards the Virgo cluster of galaxies, which is at a distance of about 20 million light years. And it's a famous cluster. It has at the center a very, very well-known galaxy called the M87 galaxy, which is famous for, amongst other reasons, the fact that this galaxy at its very center has a black hole, a very, very massive black hole, 1 billion times the mass of the sun. And that black hole, you can probably maybe just make out a jet of material that's being ejected from the center as this black hole eats everything around it. So that's what the universe around us looks like, and that is what cosmology seeks to explain. Now, so one of the first questions in my list of big questions is, what is the universe made of? And that is a question that we've been able, cosmologists, to answer to some extent over the last few decades. And the result is really pretty astonishing. Our universe, the contents of our universe are really pretty bizarre. Now, as I did mention actually briefly, a galaxy has maybe 100 billion suns, and the visible universe has about 100 billion galaxies, each with 100 billion suns, many of them, no doubt, with tens of planets. So the universe is very big, and it has a lot of stars and lots of planets. And yet, we know that all that material that we can see, which we call ordinary material, makes only about 5% of what the universe contains. So only about 5% is this huge collection of galaxies and stars, makes only about 5% of what the universe contains. And we refer to that as normal matter. It's a matter made of the atoms that we're familiar with, the same atoms that we're made of, the atoms of the periodic table of the elements. 25% of what the universe contains is something we call dark matter. And as the name indicates, well, it's just dark. So it doesn't emit light at any wavelength of the electromagnetic spectrum. It's completely dark. And yet, but we know it is there, and it is different. It's not made of ordinary atoms. It's not made, I think getting rid of the lights on the screen is probably good, because astronomy, we're blessed in astronomy. We're only second to dinosaurs in the ability to show impressive pictures. And I think they're better without the lights, if that's possible, Mark. That's perfect. So 25% of what the universe contains is this dark matter, which is not made of ordinary atoms. I'm going to tell you a lot more about it in a minute. And then the lion's share of the universe is something that we call dark energy, that was discovered, in fact, only at the turn of the 20th century. And this makes the lion's share of what the universe contains. Now, we know quite a bit about normal matter. That's what chemists study and biologists, but we know a lot less about dark matter and dark energy. And of these, we know almost nothing about dark energy. And we know so little that I'm going to show you a couple of slides, and at the end of that, you'll be more or less at the same level as the professionals who make a living from studying dark energy. So let me tell you a little bit then about dark energy. So what is this dark energy? I hope you're already suspicious when something with such a strange name like dark energy appears. You hopefully already realize that we don't know much about it. That's why we give it such a auspicious name. But the dark energy is related to the expansion of the universe. The expansion of the universe was discovered in 1929 by an American astronomer, Edwin Hubble, whom you see here in the days when people not only had blackboards in their offices, but that were allowed to smoke in their offices, a true sign of culture and civilization. And Edwin Hubble found that every galaxy around us, with the exception of Andromeda that we saw, is moving away from us at a speed that increases with distance. So where every galaxy he looked at was rushing away from us, and clearly that implies that the universe is expanding. Now, there's no reason to be alarmed. It's not just that everybody's moving away from us. Any other hypothetical observer in any other galaxy would see exactly the same phenomenon. It would see every other galaxy moving away from themselves. So what Hubble had discovered in 1929 was the expansion of the universe, and that's now a concept that we teach children in primary school. Now, what was then discovered 70 years later was the fact that the expansion is the universe is not only expanding, but the expansion is getting faster and faster and faster and faster. It's accelerating. The expansion of the universe is accelerating. Now, this discovery, which in fact earned the Nobel Prize in Physics in 2011 to the three colleagues who measured the accelerating expansion of the universe, is a very, very bizarre thing. It came as a real shock to physicists because if you think about it for a second, you can see why it was such a hugely disturbing discovery. If all the universe had was matter, we know that matter produces gravity, and gravity pulls, or as the Americans like to say, gravity sucks. And so the force of gravity should have been trying to slow down the expansion because gravity pulls. And yet, what was discovered was exactly the opposite, that the universe was not slowing down, but accelerating. And what that means is that there must be something of which we know very little, and which we call dark energy. Now, this dark energy is really, truly mysterious. We've really got no idea of what it is. It almost certainly has to do with our good friend, the vacuum. And the reason is this. Most of the universe is empty. It's a vacuum. And there's nothing much between one galaxy and the next, except empty space. Somehow, there's some property of empty space that's making one galaxy move away from the other one at an accelerated rate. So, although we don't know much about dark energy, it's almost certainly to do with the, well, we know it's a repulsive force that's causing the universal expansion to accelerate, and it may well have to do with the vacuum. And that's about pretty much all we know about this. So now you're as experts as my professional colleagues who spend all their waking hours trying to understand what this is. So you're not far behind, because that is really one of the big mysteries in modern physics. Now, so I want now to go back to, I hope, to dark matter, where we know a lot more about, I changed the battery yesterday, but anyway. So we know a lot more about dark matter. And let me tell you a bit about it. So dark matter, as I remind you, is matter that doesn't shine. It's completely dark. And, but we know it's there. And the reason we know it's there is pretty simple. Astronomers are very good at measuring velocities. In particular, they can measure the velocities of stars as they go round and round the center of a galaxy. That's a simple measurement to make. But when you make that measurement, you come up with a very surprising result. Namely, that the speeds at which the stars are moving round and round the center are much too large for the stars to remain in place if all that is keeping them there is the gravity of the material that we can see. So imagine a star here. It's moving at some speed, and we can calculate how much gravity is pulling on it due to the, or produced by the material that we can see, and we fall short by about a factor of 5 or so from accounting for that velocity. And that's something that was known by this gentleman here, Isaac Newton. It's a very, very simple formula that tells us that there must be more, a lot more mass in the galaxy than what we can see in the form of stars and gas clouds. Now, the other day I was in London wondering about this, and I was really lucky because I actually ran into Newton, and he's reincarnated now as a musician, and it is him. I mean, you can tell the hair is, of course, the same, but the nose is the same. The eye, the jaw is exactly the same. So he's reincarnated as a musician. He has a PhD in astronomy, by the way. That's how I know him. I don't usually hang out with these kind of celebrities, but he is an astronomer. He then explained to me the way in which these laws should be applied. And that's why I have this silly grin. I finally understood. Now, this is just one way we know about dark matter. I'll tell you the other way in a minute, but the way you should think about galaxies is just as little pools of light embedded in the centers of clumps of dark matter, which us astronomers, in our kind of slightly saintly aspirations, call halos of dark matter. So it's called a halo. It's not really a halo, it's just a clump of dark matter, and the galaxy is a little pool of light sitting in the center. Now, there's another way in which we know that the dark matter exists, and this is quite a spectacular phenomenon, the phenomenon known as gravitational lensing. So what you see here are some galaxies in a cluster, not dissimilar to the Virgo cluster that I showed you before. So the normal-looking objects here that look like are they're galaxies in a cluster. But then in addition, you can see these very weird arc-like features. Now these are also galaxies. I don't know if maybe you cannot see the laser from the back. Am I right that you don't see the laser from the back? Can you put your hands up? You can see it. Okay, good, okay. So these are actually also galaxies, but these are galaxies that are not in the cluster. These are galaxies that are a long way behind the cluster, whose light has been deflected by the gravity associated with the cluster. As the light rays go by, they get deflected, and this deflection produces a distortion of the image of the background galaxy, which gets distorted into this characteristic arc-like feature. This is an iconic image taken by the Hubble Space Telescope, and we can use the distortions of these background galaxies to weigh the galaxy cluster, and as well, how much mass does there have to be there to cause these enormous distortions of the background galaxies, and the answer is there has to be about 10 times more mass in the cluster than what we can see in the form of galaxies. So this is one of the strongest sources of evidence for the existence of dark matter. Here you see what would happen. This is an experiment we did in the laboratory the other day. Here's a field of galaxies, and we imagine putting a lump of dark matter in front of it, and you can see how the light is distorted by this phenomenon of gravitational lensing. So these lenses are exactly the phenomenon you just saw illustrated a minute ago. And it was predicted by Einstein, who wrote a letter to his friends in the days when science was done in a much more informal way than today. He just wrote he says here, dear colleagues, and he explains exactly how light is deflected by gravity. That's what E equals mc squared really means. And of course, Einstein would have been a failure today. There's no chance he would have made it to the ref or pass all the endless reviews that we have to be subjected to. His publication list would be laughable. His citations negligible, and yet he is one of the greatest scientists that humanity has ever produced. But what is the dark matter? Well, we don't know for sure. We suspect that the dark matter is some elementary particle. We know it's not ordinary matter. And the current view in cosmology is that the dark matter is some elementary particle that was produced very soon after the Big Bang, illustrated here. Here's the Big Bang. Here we are, 13.7 billion years after the Big Bang. And very soon after the Big Bang, 10 to the minus 10 seconds after the Big Bang, particles were created that would have all the required properties to be the dark matter. So the current view, the standard model of cosmology, assumes that the dark matter is some elementary particle formed very early on in the life of the universe. And in the standard model of cosmology, it's a particular type of particle called cold dark matter. And I might come back to why it's called cold later. So that is the basic assumption of modern cosmology. So that's a key assumption, that the dark matter is an elementary particle formed in the early universe, different from particles in ordinary atoms. And if you ask a physicist in the street, what is the dark matter? This is the answer that you would get. It is not everybody would agree, but 99.9% of practicing physicists would. So that we have evidence for that. But I was very surprised to realize that it's not just physicists, but also politicians. Here's Angela Merkel, the German chancellor, when she was asked, what is the dark matter? She said, well, it's a tiny little elementary particle. And now that's not a surprise. I don't know if you know, but Angela Merkel is actually a physicist. She's the wrong kind of physicist, but she's still a physicist nonetheless. So she knows the answer. And, but here's what happened when our prime minister was asked the question, what is the dark matter? And you can see here Angela Merkel was not impressed, but she quickly put her right. And here she finally understood herself what the dark matter actually is, a small particle. Now, something went wrong in the United States because, first of all, before the election, Clinton had completely the wrong answer, but she had a great master to teach her what the dark matter really is. You can see she's paying attention, and she got it. So why she lost the election beats me, because when this fellow was asked what is the dark matter, that's what he came up with. Now, Obama tried to teach him, but you can imagine what he did. So now the reason I show you this is not only I think we should all laugh at this clown, but it's not just that. The reason is this, and it goes back to the philosophical remarks I made at the beginning, that in science we use the laws of physics and we have a rigorous methodology to try and understand nature. It's not by tweeting or by telling alternative truths. It is essentially by experimentation. And this is the logo of the Royal Society, which is the sort of British Academy of Science. And I'm very fond of this logo in Latin here, which says "non lis in verba," which basically means don't believe anything that people tell you. Test it, find out by yourself. And that's exactly what we do in the physics of dark matter. We have to search for these particles, and the way to do it is through experiments. If the dark matter is what I think it is, called dark matter, then this room is full of dark matter particles, but the reason they're dark is because they don't interact with anything. They don't interact with the atoms of our body. So these particles, of which there are billions crossing every square centimeter of your body per second, these particles just go straight through, and they leave no signature, they do no harm, they just go straight through everything. And that makes it very difficult. That's why they are dark, because they don't interact. But that also makes them very difficult to detect, because you put a detector and it just goes straight through and leaves no signal. So detecting dark matter is difficult. It's a subject of experimental physics. I don't know if there are any experimental physicists in the audience, but if there may be one or two, but I would have spotted them already. I don't know if you've seen what an experimental physicist looks like. This is what an experimental physicist looks like. There is one of the most active areas in physics today is, in fact, trying to find out what the dark matter is. And there are experiments all over the world. We used to have one in North Yorkshire in a mine called the Bowlby mine. These experiments take place either in tunnels or in mines. This is a kilometer-deep mine, salt mine. And the reason for doing the experiments in hospitable places like this is to shield the very delicate detectors from all the debris that rains onto the Earth in the form of something called cosmic rays. These are particles that are continually raining on Earth, and this acts as a sort of sieve to shield the instruments, because although the dark matter interacts very weakly, it does interact, and so there's the detector there waiting for the very rare occasion when a particle of dark matter from the halo of the Milky Way will actually hit head-on an atom in the detector and make it move a little bit. And that is the basis of the detection. Now, this is the Bowlby experiment, which unfortunately has been discontinued because of lack of funding. Here's a visit that several people from Durham made there a few years ago. He was the founding director of one of the institutes in the physics department. He's now the provost of Imperial College in London. And here is Peter Ogden, in whose name the building that I showed you at the beginning, it has his name because he's a benefactor, he's a physicist. He's an alumnus of Durham University, and he was in the castle. And he loves the castle, and he has great interest in physics, so he was there looking for dark matter in the mine. Now, there's one true experimental physicist in this picture, and you can spot him very easily. He's the only person who's not smiling. And that's Neil Spooner here, who actually used to work in the mine. And I've been there many times, and I can tell you it's not fun being there at all. At any rate, the dark matter has yet to be discovered, but I think there's every hope that it will be discovered as these very sensitive instruments become ever so more sensitive. But I've devoted all my life to trying to understand what the dark matter is and why, and it's not just me, there are many people like me. And the reason is simple. It's not just a question of finding out what the universe is made of. It turns out that together with the vacuum, the dark matter is the main agent responsible for everything we see in the universe. Because, as I will argue now, in the next few minutes, it is the gravity of the dark matter that is responsible for the creation of everything we see, galaxies, stars, planets, and to a lesser extent, people. So how does this work? Well, so where do the galaxies come from? So I want to spend a few minutes telling you where galaxies come from, because this brings everything together. This brings the vacuum together with dark matter and together with what we see in the universe today. Now, to answer that question, of course, we need to go to a very early time, and in fact, almost to the beginning of time. The first time at which physicists can talk about physics and keep a straight face is very soon after the Big Bang, a decimal point and 34 seconds, and then a 1. For those of you who cannot see the bottom of the slide, that's what it says here, just a bunch of zeros. 10 to the minus 35 seconds after the beginning of our universe. This is the earliest at which the laws of physics, as we know them, apply. And as I say, it's the earliest epoch in the life of our universe when we can talk about physics and keep a straight face. Now, something very odd happened at that time. And that has to do with our good friend, the vacuum. Now, this is going to sound very odd, but I'm going to give you empirical evidence for this. According to the current view of the universe, our universe was born with an excess of this funny vacuum energy. And that excess of vacuum energy caused our universe, or a little patch of the universe, to expand very quickly, growing from the size of a pinhead to the size of a football in 10 to the minus 35 seconds or so. So our universe is a grossly inflated chunk of a much bigger thing, which we're not interested in at the moment. But this phenomenon, it goes by the name of cosmic inflation, and it then caused our universe to expand very rapidly for a very short period of time due to these quantum processes. Now, as you saw from the movie of the vacuum that I show you, the vacuum is always fluctuating. It's continuously producing matter and antimatter. It's continuously fluctuating. And what that does is something very important. These fluctuations of the vacuum, known as quantum fluctuations, seed the early universe with little inhomogeneities, very, very small inhomogeneities in which a patch of universe is slightly denser than average, another patch is slightly less dense. These are tiny, 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 almost imperceptible irregularities and reflect these quantum fluctuations of the vacuum. And the amazing proposition of contemporary cosmology is that everything in the universe came from these vacuum fluctuations. According to this inflation theory, we all grew out of these fluctuations of the vacuum. I know it sounds pretty crazy. It sounds to me every time. I talk about this all the time. And every time I say it, I think this is completely ridiculous. But let me show you the evidence in a minute. So in particular, then the dark matter comes into its own. The universe has been seeded 10 to the minus 35 seconds after the Big Bang with small fluctuations, small patches that are slightly denser than others. And then gravity can do its work, amplifying the patches that were overdense. There's an excess of gravity there because they're overdense. And as I will show you in a movie, these quantum fluctuations very soon, just through the action of dark matter gravity, structure our universe. So here's a patch of universe. It's very uniform, but it has some quantum fluctuations in it. And I'm going to let the clock tick. And you will see all that you see here is dark matter. And here's the clock ticking. But very soon, these small inhomogeneities grow. And lumps begin to appear where gravity has pulled material towards itself. And the universe goes from being very, very smooth to being very complex, very highly structured. And in fact, astronomers have a name for this. This is called the cosmic web. So the universe goes from very uniform, seeded only by these quantum fluctuations, to this amazing cosmic web. Now, this sounds pretty crazy, I would agree. So if you think about what I've been telling you so far, and you never heard this story before, it's just ridiculous. So what I'm telling you is that you, the sun, the Milky Way, everything in the universe came out of a fluctuation of the vacuum, of bits of matter and antimatter annihilating. Totally crazy. And I'm sure that if Einstein came in here through the door, or my newly found friend came in, I know exactly what Einstein would do. If he heard me speak here, this is what he would do. And I suspect that what Newton would do is he would say, I'd rather be a musician rather than a physicist if you think that's the way the universe was formed. But I go back to the key concept of this lecture. In physics, we have a methodology, and the idea is that you can put forward crazy notions. Doesn't really matter how crazy they are, so long as you can verify them or disprove them. You get paid at the end of the month. If you, as a physicist, make a crazy proposition, nobody's going to fire you, so long as the proposition is testable. It turns out that this fairly crazy stuff I've been telling you about so far is actually testable. And I'm now going to tell you how the test happens. So, how do we test this? Well, first of all, the Big Bang was very hot. It's actually called the hot Big Bang. There was a lot of radiation produced in the early universe that made the early universe very hot. Cosmic inflation happened 10 to the minus 35 seconds. You see in this cartoon, this little bit here corresponds to cosmic inflation, and then the universe had a little hiccup and then started expanding at a much more leisurely rate. The early Big Bang was very hot, radiation was being produced, and then something very important happened when the universe was 350,000 years old. That's actually very young by the scale of the universe, because today the universe is 13.7 billion years old. So if you scale to a human lifespan, 350,000 years of cosmic history would correspond to one day in the life of a human. So when the universe was very young, just a day old, something very important happened. And that is that the heat of the Big Bang was able to escape. Before that, the radiation of the Big Bang was trapped here, colliding with particles. But by the time the universe was 350,000 years old, the sort of fog of the early Big Bang lifted, and the radiation was free to escape. This is the first light of the universe, and this is light that has been propagating since then, and it brings us information about the conditions that prevail in the baby universe. So as the universe has expanded, this radiation has cooled. It was extremely hot, billions, trillions of degrees. Today, the universe is so old that this radiation has cooled to a mere 2.7 degrees above absolute zero. That's just because the universe expands, the radiation cools. Now, amazingly, this radiation was discovered in 1964 by these two chaps, Bob Wilson and Arno Penzias, using a very rudimentary instrument which they had built not to discover the Big Bang. Simply, they were radio astronomers, or they become radio astronomers. They wanted to detect radio waves from the sun, and they were extremely annoyed when they realized that they couldn't zero their instrument, because wherever they pointed it in the sky, they had a residual energy that they were detecting at a temperature of 2.7 degrees above absolute zero. And what they had completely accidentally stumbled upon was the evidence of the Big Bang. It was this light, the first light of the Big Bang, which had been propagating freely until it hit this instrument. But by the way, if you go outside, if you're feeling depressed someday, I mean, people sometimes do that, all you need to do is step outside, and it doesn't even matter if it's cloudy, put your hand out like this, and you will be intercepting about 100 particles of light per second, per square centimeter, that had been propagating since the Big Bang, and the first thing they encountered in their journey is your hand. So there are about 100 photons, as we call them, per square centimeter per second, crossing any surface today, and these chaps were very lucky to find them with their radio telescope, and of course they got the Nobel Prize for that. Now, from our perspective, this is crucial, because this light is the farthest away we can see, or the earliest we can see in the life of the universe, and it brings us information about conditions that prevailed when the universe was a human equivalent of one day old. And this is the tool that we use to test our theories. So, if quantum fluctuations were present, the precursors, I argue, of galaxies, 10 to the minus 35 seconds after the Big Bang, as the universe expands, these quantum fluctuations will evolve. They just get bigger. As the universe gets bigger, these quantum fluctuations get bigger. And then, by the time the universe is 350,000 years old, these fluctuations would be reflected in the temperature of this radiation discovered by Penzias and Wilson. By the way, it's called the microwave background radiation because it's so cold, it appears as microwaves, just like in your microwave oven. That's the same kind of wavelength. It's called the microwave background, that light from the Big Bang. And these quantum fluctuations would then affect the temperature of that radiation ever so slightly. So theories predicted in the 1980s that the radiation should have small irregularities in temperature. It should have hot and cold spots that reflect these quantum fluctuations amplified slightly in the early phases of the Big Bang. And in fact, using the laws of physics, physicists were able to calculate details about this temperature pattern that we should see in the microwave background radiation. The details don't matter of this curve. For the specialists here, this is just a measure of the temperature difference between 2 points on the sky as a function of how separated they are. The details don't really matter. The point is that the prediction from theorists was not just a line, it has some structure in it. 1992, April 22nd to be precise, was a landmark, a historical day in human knowledge, in human understanding, because an American satellite called COBE published this picture, which has now become one of the most iconic pictures in physics. And this is a map of the temperature of this microwave background radiation. So what you see here is this radiation that has been propagating throughout most of the life of the universe. And what you can see is that it's not uniform. This is a temperature map. It has hot and cold spots. This discovery made headline news in the days when newspapers, first of all, still existed in paper. This is the Independent that no longer exists as paper. You can only look at it in a computer. And this was the front cover of the Independent on Friday, the 24th of April of 1992. How the universe began. Now, excuse me if you think I'm going to brag a little bit. Hope you forgive me for this, but I made personally a contribution to this, which is highlighted here. Those in the front rows will be able to see what it says. It says, Carlos Frenk, an astronomer at Durham University, said yesterday, "Oh, wow." That was my great contribution to this discovery, my great contribution to human culture. And my wife knows when I die that my epitaph will say, "Oh, wow." And I had a good reason for saying, "Oh, wow." It's the only time I said it in public to the press, but it really was a wow moment. Well, there are two reasons. One is this was NASA. NASA are very good at PR, so the news were embargoed until midnight Washington time, which happens to be 6 a.m. Durham time. My phone rang at 6 a.m., and I get this American reporter at the other end saying, "Dr. Frenk, what do you think about the discovery of fluctuations in microwave background? Well, what do you say at 6 a.m.? Oh, wow." But actually, it was really wow. And it turns out that this earned George Smoot the Nobel Prize in Physics in 2006. And I actually had dinner, and more than dinner, I took him out to a bar in Italy where we were both teaching in February that year. And I tried my best because I knew the experiment was there. I knew he had to have something. I took him to the best restaurant in Sicily, to the best bars, all sorts of things I wouldn't dare tell you here about, and I got not a peep out of him because he was fully aware that what he had discovered was not something to talk about to a colleague. It was one of the most important discoveries in science ever. 10 years later, NASA launched another satellite called the WMAP satellite, which measured the same thing, but with greater resolution. And then the Europeans, always trying to catch up, yet 10 years later, finally caught up with the Planck satellite, which has made even more precise measurements of these fluctuations. But you see here, this patch is there, there's the same thing, but with much higher resolution. Now, I should stress that these measurements are extremely delicate. These little patches of hot and cold spots that you see here differ in temperature by 1 part in 100,000. So even though imaging techniques makes this look very obvious, the difference in the temperature between a hot and a cold patch is only 1 part in 100,000. So these are very, very delicate instruments. But the key point is that this was the prediction for some quantity that describes these temperature fluctuations made in the 1980s. Actually, the first ideas were there in the 1970s. These are the data from the Planck satellite. So what you see here in green are the predictions of theorists, predictions that involve quantum fluctuations, that involve inflation, that involve cold dark matter. And the red dots with arrow bars are the experimental measurements. And as you can see, the agreement is just remarkable. And so I usually pause when I show this plot because it may not look like much, but to me, this is one of the greatest achievements ever of humanity. And we need to ask ourselves, how come in a little corner of a galaxy that looks like any other galaxy, a species of animal has evolved, capable, on the one hand, of designing theories to describe what happened at the beginning of the world, that's the green line, and the same species of animal has also the capability to build machines that they launch outside from the planet, capable of making these very delicate measurements. So to me, this is the physics equivalent of a, probably even better than a Rembrandt picture or a Beethoven symphony. I think, to me, human ingenuity doesn't get any better than this. And certainly, physics doesn't get any better than this. So, what does this tell us? It doesn't prove that there was inflation. It doesn't prove that there were quantum fluctuations, but it tells us that the description of our universe, as we know it, based on these crazy ideas, seems to be compatible with everything we can measure. And what we're looking at here, I remind you, are properties of our universe when it was the human equivalent of 1 day old. Now, so these small fluctuations then provide the initial conditions for the formation of galaxies. Time is getting on, so I'm now going to compress 13.3 billion years of cosmic evolution just in a few minutes. So how do we go from these initial conditions? How do we know that these really made galaxies? Well, we have to calculate. We have the laws of physics. We can calculate the evolution of these small fluctuations according to the laws of physics. And it turns out that you need a big computer to do that, and that's one of the things we do here in Durham. We have one of the biggest supercomputers in the country dedicated to cosmology. And what we do goes by the name either of making virtual universes or of computer simulations of the universe. So the way this works is in principle very simple. We have the initial conditions. We can see them imprinted in the microwave background radiation. And then we have to make assumptions, for example, about the nature of the dark matter. We have to assume, for instance, that the dark matter is called dark matter. And then what we do is we program these big computers. We teach them how to solve the laws of physics. And I can promise you it's much easier to teach a computer to solve the equations of relativity than it is an undergraduate. And moreover, computers never answer back. They just give you the answer, and they work on weekends as well. And so we program the computer with the laws of physics. We teach the computer how to solve them. And then together with and we know the initial conditions, we assume something about the dark matter, and we let them compute, often for weeks or months or even years, and we see what comes out. So now I'm going to show you some results of these computer simulations where you will see first the evolution of the halo of a galaxy like the Milky Way, how it grows from quantum fluctuations to the halo of a galaxy like the Milky Way. So here are these quantum fluctuations that I've been talking about. This is just dark matter, and you see how the dark matter very rapidly amplifies these small 1 part in 100,000 fluctuations, creating lumps that grow bigger and bigger because, as I said before, gravity sucks. So a lump of matter here attracts other lumps, which then flow along this small-scale version of the cosmic web, produce amazingly beautiful patterns. And you see here a lump being attracted by another lump and growing larger and larger as this process of what we know as mergers proceeds. And we call this hierarchical clustering because, as you can see, structure goes from being very small to getting increasingly large. And here there's going to be a very big merger of several of these lumps that are assembling the halo in which eventually gases that follow the gravity of the dark matter will eventually, spinning gases, cool and collapse, become unstable, and make stars. So this is a simulation of dark matter. And now I'm going to show you what the universe would look like if you were able to wear glasses that allow you to see the dark matter, and if you were able to travel very, 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 very fast indeed. So this is now the present day, and this is a picture of the cosmic web. So you can see the huge, we're going extremely fast here, many, many billions of times the speed of light. So you can see the huge richness of structure that the universe has made out of these quantum fluctuations. And I remind you, these simulations are particularly simple. There's only dark matter, only gravity, and this is what the solution to the laws of gravity from these initial conditions in a universe made of cold dark matter would produce. And now the modern, today, after many years of trying really hard, we're finally able to make simulations, not just of the dark matter, as the ones I just showed you, but also of the visible material in the universe. So these are much more complicated simulations, taking years to get to what I'm about to show you. And what you see here is the evolution, again, from quantum fluctuations, not just of dark matter, but also of gas and stars. So we start as before. This is, again, just dark matter. We're going to cut to gas in a minute. And you see, again, the story that I just told you of how the universe becomes increasingly structured just because of the action of gravity. So this is just as before. Now we're going to cut to gas. Now the gas is spinning. Everything in the universe is spinning. And it is attracted by gravity. You don't see the gravity here. We're just focusing on the gas. But now you can see what the gas has done. It makes these structures that look like spiral disks. They're also building up. They're becoming larger and larger by merging of fragments. And here we cut to stars. So this is what came out of our computer, just assuming inflation, quantum fluctuations, cold dark matter, and the laws of physics. Now, this was not quite the present day. We're now going to continue the simulation to the present day. Here you see these beautiful patterns that emerge. Naturally, I mean, this is a computer simulation. There's no computer graphics here. Well, there's computer graphics, but there's no animation of any sort. This is just what came out of the computer. We cut back to stars, and now we're going to zoom out because one can simulate, of course, not just one galaxy, but a whole population of galaxies. And we spend a lot of our time at the Institute trying to understand the properties of these galaxies and compare them to what our observational colleagues see in the real universe. This is just a small gallery of pictures. Those of you who are familiar with galaxies in the real universe may think I took this out of the Hubble Atlas. I didn't. This is what the computer produced out of these crazy ideas that I've been telling you about so far. So I'm almost done. And what I've been telling you about today is quite a remarkable story. A story that begins 10 to the minus 35 seconds after the Big Bang, when the universe underwent a period that we don't fully understand, known as cosmic inflation. I show you the evidence for why inflation probably happened. We don't fully understand what caused the universe to inflate. It's probably related to vacuum energy. And these fluctuating quantum fields seeded the universe with small fluctuations that are then seen directly in the temperature structure of the first light of the universe, of the microwave background radiation. And computed simulations then show how these small fluctuations are amplified by gravity and how the rest of cosmic structure just follows according to the simple laws of physics. And of course, our simulations today allow us to simulate galaxies and stars. It's just a matter of time before we can simulate planets. And I would say it's a matter of a little bit more time before we can simulate humans and probably consciousness. But I'm not going to go that far today. So is this the end of the story? Well, it's the end of one story, but it's the beginning of the most interesting part of the story. because there are many things we don't understand. So let me finish off with one of my favorite pictures. It's the Garden of Early Delight by a 15th century German painter, Hieronymus Bosch, who painted this triptych. Here in the center is paradise, earth, here is hell, and here is paradise. And I think this nicely summarizes where we are today. So here on Earth, I put the question of what is the dark matter. I think I know what it is. It's just a matter of getting my colleagues to agree with me. The dark matter is almost certainly one of these elementary particles that I talked about. And the challenge now is for physicists to experimentally discover these particles. And the technology being deployed, sadly not in our country, but in many other countries, in the US, in France, Switzerland, China, and India, is now getting so sophisticated that I think it's just a matter of time before the dark matter is discovered. I would say it should be discovered within the next 5 years or so. Mind you, I've been saying that for the last 20, but now I really mean it. So that's here on the paradise, on the earth. In hell, I will put the question of the dark energy. That is truly a hellish question. We have no idea what the dark energy is, and I personally don't even see where we're going to go looking for it. So I think this will need a new Einstein who comes up with some completely wild idea. I don't know what it will need, but humanity has decided actually to spend many billions of dollars or pounds or euros trying to answer this question. There are all sorts of very exciting astronomical missions, that some in space, some on the ground, to try to answer the question of what is the dark energy. So Earth, what is dark matter? That's an earthly problem. Hell, what is dark energy? And I reserve for paradise the ultimate question of them all. How did our universe begin? We know there was a Big Bang, but we don't know what went bang or why it went bang. And I'll stop here.
Thank you, Carlos. I mean, breathtaking, brilliant, illuminating, and I'm sure there are many questions. So if you're going to ask a question this evening, please keep it brief, say who you are, and then ask a brief question so we can get as many questions in as possible. Are you happy to take questions in clusters of 3?
Whichever style.
Let's take 3 at a time. There's a microphone somewhere, and there's 2 people over there. Let's ask them both.
Thank you very much for that. As a philosopher who deals with ancient astronomies, the proposition that something or even everything comes out of nothing always makes me a bit nervous, I have to say. And so I was wondering whether you could quickly expand a little bit on this idea that you presented rather at the beginning, that if you take a complete vacuum, actually what you have is something completely full. Matter and antimatter. Is the idea that this really pops up, so to say, or is this the idea that this is still left no matter how much you try to get everything out?
Okay, thank you. I have 2 questions. The first question is about the future of the universe. Will the expansion of the universe continue forever, or there will be some time the universe began to shrink? And the second question is, what's the future of human beings? Can we survive from the transformation of the universe? Thank you.
And the third and final question, this gentleman over here.
My name is Steve. I just wanted to find out whether from the current knowledge of dark matter, do you foresee what will be the end of is there a cataclysmic end of the world or of the universe, basically?
Okay, so you asked me the easy questions. So first, for the philosopher. So I think your question is very, very profound, and it's difficult to answer briefly because it's essentially the basis of quantum physics. So quantum physics is, again, a world of marvel, of very non-intuitive concepts. The one that I talked about, this fluctuating vacuum, is one such counterintuitive concept, but it is the basis of quantum physics. So there's something called the Heisenberg uncertainty principle that tells you that the laws of conservation of energy and everything we know about our universe are perfectly compatible with small packets of energy appearing so long as they disappear fast enough that they don't violate this Heisenberg principle. So this fluctuating nature of the vacuum is something that is not just compatible with the laws of quantum mechanics. In a way, it's actually predicted by quantum mechanics. And unfortunately, it's a counterintuitive idea, like much of quantum mechanics and indeed like much of relativity. When I first encountered this concept, I must admit, and when I was a young undergrad in physics, it actually kept me awake at night because I just couldn't understand how this could be. But it is, and the best thing I can say in support of this obviously upsetting and disconcerting concepts is that there is this Casimir effect that I mentioned earlier. It's an experiment that you can carry out in which the way it works is that you have a vacuum, or as good a vacuum as one can make, and put a small, very thin metal plate, and you can actually measure how the plate vibrates as these quantum fluctuations impact on it. So it's something that's experimentally measured, and it's just built into the fabric of our universe. So the fabric of the world is counterintuitive, and then we understand why it is so strange, and that is because we are much bigger than the scale of quantum phenomena. These quantum processes occur on scales even much smaller than an atom. And so we're not familiar with that very small scale world any more than we're not familiar really in our everyday experience with the world of galaxies. So that's why it is counterintuitive. So that's the best explanation I can give you at 9 p.m. I think to get deeper into this, you really have to study quantum mechanics in some more detail. But suffice it to say that there is experimental evidence that these quantum fluctuations, this energy popping out of nowhere, actually is a part of our universe, the universe in which we live. Now, the next question was about the long-range forecast for our universe. Now, we're not so good at that. We're not as good as the BBC are at predicting the weather. And the reason is this. You question about what the long-range future of the universe is. Will the universe expand forever, or will it reach a maximum size and then recollapse? The answer to that question depends on one thing and one thing only, and that is the nature of the dark energy. And because we don't know what the dark energy is, we cannot give an answer to that question that is based on our current knowledge of physics. Now, so there is, of course, a hypothesis for what the dark energy might be. It actually goes back to Einstein. So the current standard model of cosmology, which is very unsatisfactory in this respect, assumes that the dark energy is some constant form of energy that has always been the same since the beginning of the universe, and that doesn't change from one place to another. So it's a very gross simplification, almost certainly incorrect. But if the dark energy is that simple cosmological constant form of energy, then we know what will happen. And what will happen is the universe expansion, the expansion will get faster and faster and faster. We'll go into something called the Big Rip, where all matter will be pulled apart from every other part of matter. And essentially, the universe will just go into a wild expansion faster than the speed of light. And our future then looks kind of rather grim. Now, but that won't happen for many, many trillions of years from now. More sooner than that, and something may perhaps applies to the third question, is what the fate of a small part of the universe is. And that we know. So I said in passing, and slightly cryptically, that Hubble found that every galaxy except one, big galaxy, there's little ones as well, but except one big galaxy, Andromeda, is moving away from us. Andromeda is coming towards us. Unlike every other big galaxy. And the reason for that is the gravity of the dark matter attached to Andromeda and to ourselves has already arrested the expansion of the initial expansion of one relative to the other. Andromeda is now falling towards us. And in about 4.5 billion years, which coincidentally is also roughly the lifespan of the sun, what the sun has left before it runs out of nuclear fuel, in about 4.5 to 5 billion years, the us and the Milky Way and Andromeda will collide. And I really wish I lived long enough to see this, because it's going to be spectacular. This collision is going to wake up the massive black hole. The Milky Way has one of these supermassive black holes, which happens to be underdeveloped. It's about 100 times smaller than it should be. It's just waiting for Andromeda to hit us. And then the spiral disk of our Milky Way will be disrupted. The gas will flow to the center. There'll be enormous fireworks as the black hole eats everything around it, producing a quasar. And that, most certainly, the Earth will be detached from the sun, and that'll be the end of things as we know them. And I'm just working with a student on an even closer cataclysmic phenomenon. I don't want to go into great detail about this, because I'm actually doing the calculations as we speak. I think the doomsday is probably closer than we think, because recently there's a galaxy which is inside our own galaxy orbiting, called the Large Magellanic Cloud, and recently it was measured to be much bigger than we thought it was, and when that hits the center of the Milky Way, it might do the same thing. So you must understand the universe as a dynamic entity, in many ways hostile and violent. Collisions and very energetic phenomena are the norm. And so going back to the other question as to what is the future of life, I'm just reminded of a great sentence that one of the most brilliant physicists ever uttered in Chicago at coffee time, Enrico Fermi, in the 1930s. He walked into a room full of colleagues having coffee, stood on a table, and he shouted, "Where's everyone?" And what he meant by that is, where are other forms of life in the cosmos? Why have we not heard from them? It may well be that life is just short-lived, and that there's not enough time for civilizations to become mature enough to be able to communicate with other civilizations, because unless that's the case, the universe should be teeming with life. And so, however, we're entering now into the realm of speculation. I think it is very interesting that we have no evidence of life outside our own planet, whether that's because our technology is still very primitive, or because in our violent universe it's very difficult for a civilization to grow mature enough to develop the technology required, for example, for interplanetary travel, whether there's just not enough time for that before some cataclysm wipes us out. So enjoy it while you can.
More questions? Any physicists in the front want to ask anything pressing, or you've been in these discussions before? So let's go to the gentleman over there. In fact, there are two people. We'll take them one after another.
So in your simulations, I was wondering how sensitive the result is to the pattern of the original cosmic microwave background. And if you manipulate that pattern, do you get different results in the simulation? And can that tell you about how special the original quantum fluctuations are?
Aristotle claimed that nature abhors a vacuum because nothing cannot exist. As you suggest, the vacuum isn't nothing, and consequently, everything hasn't come from nothing. And it seems as though you're saying the universe existed because there wasn't nothing before there was everything.
One last question. Anyone here? Yes. Just take the mic forward. Thank you.
I'm a music and history of art student, and something we learnt in history of art, we were studying ancient Chinese art. The religion Taoism, they believed in this energy of fluctuating between the yin and the yang, and that sounds very similar to what you're describing, and I just think that's really interesting. Do you have any ideas about that?
So let me answer them in inverse order. So, as I said, at the beginning, we're not the only people to worry about these things, and there are parallels, and some actually immensely appetizing and suggestive. So the yin and yang is one. There is actually in Durham a group of people who are investigating one of the great thinkers of the 12th century, Robert Grosseteste, who visited Durham. He was a clergyman, as most thinkers were in those days, visited Durham briefly, And they've discovered manuscripts by Grosse test where phenomena not dissimilar to the Big Bang are described. But I think one can make analogies, and there are many like this, but I think I want to just highlight the uniqueness of the way in which physics approaches these problems, because we have a methodology limited. It is limited, I'll have to admit. I mean, we cannot answer every question. And here I put, how did the universe begin? And I made a mistake when I said, we don't know what went bang. That's true. But then I said, and we don't know why it went bang. That's not part of physics. In physics, we never ask why. So that was a slip of the tongue. So our methodology is it's what it is. It's limited, but it's immensely powerful. But I agree with you that not only in China, but even here with Grosse test, if you look at some of the creation myths of the Mayans, they all have things in common that we can establish analogies. But here, the onus is on empirical demonstration of your propositions. Now, I love the syllogism at the end. Now, so perhaps my mistake was to, in order to make the title sound attractive, I used the word nothing. But I explained really that nothing in physics means something quite specific, and it is just the vacuum. I like to think of the vacuum as nothing, but again, I'd resort to a similar answer to the one I just given, that in physics we try to be precise with our concepts and the words that we use. Some of the words we use come from everyday life. I mean, energy, for example, but it may mean something completely different to a yin and yang a viewpoint. Energy might mean something very different from what we mean by energy in physics, because energy in physics is described by some mathematical equation, has a very defined, well-defined concept. Now, so I slipped, I must admit, in using the word nothing to describe the vacuum, because the word nothing is a word from the common language, which has a well-defined concept. In physics, it means something slightly different. It just means the vacuum. So I think that with that, I was slightly imprecise in borrowing this word, but of course I was alluding to Aristotle myself, and I do think that eventually everything came from nothing when we, by nothing, understand the fluctuations of the vacuum. In that limited sense, that is where I say everything came from nothing. Now, to the first question, I know the answer, but I forgot the question. So can you just quickly remind me the gist of the question? Oh yes. So it's a very good question. Until so when we had just naive theoretical ideas about the initial conditions of the universe before, when I started my career, for example, we were already doing simulations of the universe before these microwave background fluctuations were discovered. And so one could create universes with very different properties, because we were kind of in a vacuum, using the word in its normal sense. We did not have these experimental constraints that we have nowadays. So if the fluctuations were different, then we would create universes. I mean, I have done lots of failed universes before these measurements that I was talking about before. I was an expert in making wrong universes because we didn't have any experimental handle on the nature of the fluctuations. So prior to 1992, or in fact, it was mostly with WMAP, it was fun because we could write lots of papers. We just run a different simulation with different parameters and you get a different universe. So now the problem is very, very well constrained because these measurements are of exquisite accuracy. You saw the size of the error bars, they're tiny. And for example, we know the parameters that describe a universe, like the amount of dark matter. I put 25%. We actually know that number to a precision of better than 1%. We know the expansion rate of the universe to a precision also better than 1%, and so on. So now there's very little freedom. The only freedom comes into the assumption about the nature of the dark matter, and where we assume cold dark matter, but it could be something else. And there's a huge, very rich vein of research that tries to make model universes with different kinds of dark matter. We do that here as well. And that's the only freedom we're left with. So, but yes, in principle, now how unique were these fluctuations? I think it's a profound question because, and I don't have the answer. And if anybody tries to give you an answer, don't believe them. And I know why I don't have the answer. And that is to do with the nature of inflation. And that's because, I mean, physics is wonderful, and you can see I love physics, but it's limited. And we know where our current understanding breaks down. And it breaks down at a time when these quantum fluctuations are being created. And we know why it breaks down. Today, in the universe today, we have two separate branches of physics. We have quantum physics, which describes quantum fluctuations and the world of the subatomic particles, and then we have general relativity that describes the universe as a whole. Now, these two coexist peacefully. They don't get in the way of one another because quantum processes have to do with very small things. Relativity has to do with very big things. So the two theories live happily side by side. They don't interfere with one another. However, if we go back to close to the Big Bang, where the quantum fluctuations are being produced, that's no longer true. And that, at that time, one can just show from the equations that quantum phenomena and relativistic phenomena are both equally important on the scales of the tiny primordial universe. And we do not have a theory that unifies quantum physics with general relativity. Many great thinkers have wasted their lives. Einstein, the first one. Einstein did all his work until he was 25, and then or 27, and then he stopped because he was in the search for quantum gravity. Even though he didn't believe in quantum mechanics, that's why he's sticking his tongue out. In spite of that, he wasted 30, 40 years of his life in the search for a theory that would unify relativity with quantum physics and failed. Stephen Hawking, he's still alive, so I don't want to say he's failed, but he's a friend of mine. But he, too, has not succeeded, let me put it like that, in finding such a theory. So until we have a theory of quantum gravity, I can't even begin to answer that question, and therefore I cannot answer your question of how unique are these quantum fluctuations. We don't know. We don't have the tools to answer.
Three more? Sure. Okay. Any at the back? Yeah, let's go to the back first. Right at the back.
Okay, so I would like to ask a very peculiar question. Isn't there a tension between the idea of the Big Bang and the acceleration of the expansion of the universe? Because, you know, if we measure the current speed, and this is the result of a very lengthy acceleration process, then at the beginning, the expansion should be very slow rather than very fast. But the Big Bang idea is based on the consideration that it was very fast at the beginning and it slowed down. So do you see any tension between these two considerations?
Okay. Coming forward. Yeah. Lady here, yeah.
Can you say anything about current understanding about the shape of the universe and whether it's infinite? The shape of the universe and whether it's infinite, and could it be true that it's sprouting baby universes? Could it be true that? And could it be true that we're sprouting baby universes?
Okay, 20 years ago probably, you know, I saw you in TV when you had discussion about, you know, Jeff ending, you know, suggestion that Big Bang start from different shape that it's usually we imagine, yes, that it's like point, and when Jeffrey said that, you know, it was like flat, you know, area or something, you know, because I'm not, you know, specialist on the, I am, you know, like, my imagination is working this way, yes, shapes. Could you explain me, you know, why you think that can't be this shape, flat, you know, shape on, you know, its point? Mm-hmm. Yep. Thank you.
Anyone else would be really unhappy if they didn't ask a question tonight? Good. Oh yes, he'd be very unhappy. So that will take a fourth and final question for this evening.
Got to remember them.
Yeah, how are you doing all right so far?
Yeah.
It's quite a short question, but is it possible for another Big Bang to occur either within this universe or outside of it?
Actually, interestingly, these three questions are the same. So different aspects of the answer is the same. There are different aspects. So let me first answer the very interesting question from the back. The question was whether if the universe, the expansion of the universe is accelerating, then today, as we measure it to be, then shouldn't it have been slower in the past? And therefore, is that in contradiction with the idea of the Big Bang? Now, so that's a very interesting question. And the answer is this. This dark energy has only become important quite recently, in the last about 4 billion years. Before, it was not, didn't play any important dynamical role. And the reason is quite simple, that if it is a cosmological constant, and we have no evidence that it is anything else, then this is a constant energy density. So it's always the same from the Big Bang to the present. So that's what it is. But then the energy in matter, that it increases towards the past, because as the density increases towards the Big Bang, then the gravity becomes stronger and stronger. So for the first 10 billion years of the universe, all that mattered was the gravity. All that mattered was the gravity of the mass, particularly of the dark matter. And during that first 10 billion years, the expansion was actually slowing down. And then eventually, as the density fell, the importance of gravity declined, and then this energy density that was just sitting there constant, waiting for its chance to pounced about 3 billion years ago, and it's taken over the expansion of the universe. So there's no contradiction. So it's in fact actually quite an integral part of the Big Bang. Now let me turn now to the other three questions, which are very profound. And we have an expert here on the multiverse sitting over there, Charles Jenks. He's not a physicist, he's actually a landscape architect, but he has made artistic representations of what we're talking about here. So the question is, first of all, what shape does a universe have? Is there only one universe? Will it expand indefinitely? Is it infinite or is it finite? Now, the question, let me take the easy part, which is the universe infinite or finite? Now that, again, we don't know for sure, but the answer to that is also related to whatever the dark energy is. But to me, the most likely, and this is just, I'm guessing here, answer to the question is the universe must be infinite, because that's the only thing that actually makes sense. And if the dark energy is something simple, like the cosmological constant, then the universe will be infinite and will expand indefinitely in a rather dramatic way in this big rip. But now, even the question of an infinite universe is enough to keep you awake at night. So if the quantum fluctuations didn't do it, this is guaranteed to do it. Because if the universe is infinite, that means that everything happens everywhere, and not just once, but an infinite number of times. So somewhere in this infinite universe, there's a place just like this, where I'm wearing your glasses and you're wearing mine, and not just one, an infinite number of them. But the interesting thing is that the cosmic histories immediately diverge. So anyway, so now, that's intimately linked to the idea of baby universes. And inflation is, in fact, intimately linked to the multiverse and to the baby universe. And the reason, if you remember, when I had my cartoon of the inflation, I had something that said, I can't remember what it said, blah or something. And I said, here's a patch of universe. Our visible universe is a grossly inflated patch of a much bigger thing. What is the bigger thing? The bigger thing is the multiverse. And inflation is perfectly compatible with the view that it's not just us, who is not our own patch, or just our patch that inflated. Inflation will probably have happened in an infinite number of places, and it is happening today. So this idea of baby universes is intimately comfortable with the idea of inflation. However, and I'm going to come to your question in a second, however, there is a big proviso, namely those other patches of multiverse are not really interesting to me because we'll never know about them. They are beyond what we call our causal sphere. So we will never know if they exist or we'll never get any information about them. So from the point of view of a physicist, it's an idea nice to entertain, as is the idea that the universe is infinite, but it is of no practical consequences because we'll never be any the wiser. I think we'll never get empirical evidence, and if I stick to my word of being an empiricist as a physicist, then it should be of no interest to me. Of course, intellectually, it is fascinating. Now, to what I said on television, I don't remember, but a long time ago, but I used to say something was wrong and misleading. And that's how I was taught until I thought about it. Because one imagines the Big Bang as a point. Actually, it was not a point. It was never a point. The Big Bang was, if it is infinite today, was always infinite. And so when you see movies of something exploding, and even in my previous cartoon, that it all starts at a point, that's absolutely misleading. The universe was never a point. Our visible universe was a point. So everything we can see in the universe today, if you run the movie backwards, everything will be in a point. But because there's much more universe besides what we can see, that, and if it is infinite, as I would think it is, then the Big Bang was infinite. The Big Bang happened everywhere. And it, because of quantum effects, would not happen exactly at the same time. And that's why I was saying that many different patches of universe would have inflated. And we probably almost certainly live in a multiverse. And so this idea that we started off from a point is misleading. The material we see today was at a point, but there's a lot more stuff beyond that point. And the universe, if it's infinite today, it was always infinite. And so I think if you were not going to be kept awake by the idea of nothing coming, of everything coming out of nothing, this should keep you awake. The idea that the universe is infinite, and then there's a very large number of parallel universes, you want to call them like that. There are actually very respectable physicists who spend their time trying to count how many of these island universes there would be. This is something you can calculate. It's 10 to 160 or something, the best number so far, a very large number. And I think on this note of island universes, given that we're in Durham, it's a good place to finish, because the first idea of an island universe came from somebody in Durham, a professor here of many things, including cosmology, Thomas Wright of Durham. You can learn all about him in the library, who in the 18th century was the first person to think that there may be more than one universe. He was thinking more of galaxies, and now the modern version is that it is other universes.
If I can quote you, Carlos, as a way of ending, wow. I mean, what is so engaging about the way you deliver these lectures is not just the sort of brilliance of the account, the illumination, the theoretical contextualization and methodology, but your enthusiasm, your passion, your just engagement with the subject matter. It's infectious. I'm not a physicist, a humble social scientist, but that enthusiasm is infectious and ripples through the audience. So on behalf of everyone here, let's thank you enormously for coming this evening.